Hey class, Mr. Hofstad here with our fifth unit. Starting off, we are going to spend the next couple of weeks talking about circular motion and this concept that we're all familiar with, gravity. But we're going to look at it with a little bit more detail and scrutiny and focus in on sort of how and why gravity really exists at a basic level anyways. So to get us in the mood for this new unit, we have our comics as per usual, and this first one, you can see Isaac Newton was about to discover gravity because we all know that he discovered it when an apple fell on his head. I don't know if there's a lot of truth to that story, but there's probably about as much truth to that as there is to William Tell. He's a famous archer. Some people think that he kind of created this idea of Robin Hood, right? Both from England and around the same time. But obviously, the perfect shot from William Tell prevented Isaac Newton from having his epiphany or his revelation of gravity. And this next one, super exciting that we get to look at space and orbits and lots of cool astronomy in this unit. We don't go super deep into it, unfortunately, but it is our closest thing to astronomy in our high school physics. So very exciting nonetheless. And here we have a great cartoon about scientists tinkering with this super fancy probe and the dreaded flashing 12 o'clock. We have all experienced that with our alarm clocks or our power out on our microwaves or ovens, whatever it is. And apparently these scientists are having the same problem. So it doesn't matter what level your education is at, technology can still be frustrating, as we all know. All right, let's get started with lesson 1. So we have kinematics of circular motion. So if we think back to our first and second unit on kinematics, kinematics is all about motion, right? Whether that's speed or acceleration. And here we're going to look at the kinematics of objects that are moving in circles. So this whole unit is focused on circular motion and then connecting circular motion to gravitation. So this is a good starting point. So for an object to accelerate, we need to have the velocity changing. We know that velocity is a vector from our first unit. So there's two ways to change velocity. So if we're having acceleration, we're changing velocity either by changing its magnitude, right? That's speeding up or slowing down, changing how much velocity we really have. Or this is where we're getting into new stuff, right? Unit 1, this is the type of acceleration we really focused on in our first 2 units. Whereas here, we're looking at an acceleration where all we're doing is changing the direction. So this first one is our regular acceleration. The second one, the change in direction of a velocity vector, is what we call centripetal acceleration. And we'll see shortly that you can have acceleration without changing the speed at all, as long as you're constantly changing the direction of that velocity vector. So we're focusing this unit on this centripetal acceleration. So we will study motion that stays at the same speed, so constant speed, 0 of our regular acceleration, no speeding up or slowing down. But we are having a change in acceleration, which introduces centripetal acceleration. So centripetal, kind of think of it directed towards the center. We'll get into that as well. So whenever something has the same speed, but a change in direction, we call that uniform circular motion. And that is going to be a buzzword for us this unit. So uniform acceleration has this uniform circular motion, involves centripetal acceleration. Without our, I don't know if you would want to call it conventional acceleration or our previous definition of acceleration. So our speed is not changing in magnitude, we're only changing the direction. All right, here we're getting into our new formulas, which are under our circular motion section of our formula sheet. So if we consider an object moving in a circle of radius r, right, where the radius is the distance from the center of the circle to its outside, right? So the radius is r, and the speed it's moving at, which is constant, is rv. We get this nice fancy definition of speed, where the 2 pi is related to the circle's path, right? If we think about the blank in here, our circumference, right, of the circle. So that's kind of the path along the edge or the circumference of circle, right? And that's the distance that this object's moving. So that's where 2 pi r is coming from. It's our circumference of circle. You might have to revisit your junior high or elementary math if you're forgetting about circumference. I think it's covered in high school as well, but it's introduced for sure already way back then. Sorry for the elementary school writing and the spelling mistakes, but we're working with limited technology. So we got circumference, and on the bottom we have time, which is the period of one lap or one rotation. So we have circumference, which is like our distance that we're traveling, divided by our period, which is like our time. Distance over time is speed. We're just changing it to be circular rather than linear. So 2 pi r is the circumference of a circle, and capital T, so focus in on the capital. Whenever you see a capital T, we know we're working with period. So pay attention to uppercase, lowercase, and spelling. All right, so period will always be the time it takes to do one rotation or one revolution or one lap, however you want to think about it. So we got our speed is 2 pi r over period. Now velocity, even though the speed remains constant, the velocity is constantly changing. That's because the velocity vector is always tangent to the circle. So however you want to imagine this, probably the easiest one is to imagine this is a yo-yo and you're holding it on by a string and spinning it around you. The speed of the yo-yo at any point in time is always going to be completely perpendicular from the center of where you're holding it, or tangent to the circular path that it's on. Right? This yo-yo is never going to be actually speeding up towards me, right? It's not able to speed up away from me. It's always has this velocity directed perpendicular from this bisecting line towards me in the center and tangent to the circular path. So that's going to be super important. Velocity is always tangent to the circle of its path, and the direction of the velocity vector is the direction that the object would move if it was let go. So if I let go of my yo-yo right here, it's going to fly off in that direction based on Newton's first law, which is inertia. Right? If there's no external force acting on it, it's going to either remain at rest, or in this case, moving in the same direction. Okay, let's try out our first example. We have a centrifuge spinning at 3,600 rotations or revolutions, however you want to think about it, per minute. We want to find, or we know the speed, we want to find the diameter. So we need to kind of increase our physics vocabulary, so to speak, getting into this idea of rotations per minute and period. So if we know we have 3,600 rotations per minute, right, we can, from this information, actually figure out how long it takes to undergo one rotation, right? So if we flip it top and bottom, right, we'll get 1 minute. In 1 minute, we will have done 3,600 rotations, or 3,600 rotations per minute, right? We've just rewritten it, but now we can actually get the time it takes per rotation. So if we have 1 minute, we know we have 60 seconds. Oh, that's too much. $60 seconds for 3,600 rotations. Or if we divide 60 by 3,600, we will actually get 1.667 times 10 to the negative 2 seconds per rotation. And what do we call seconds per rotation? That's going to be our period. All right, period is always how many seconds per rotation. So, big, long, complicated way to get to period, which of course is our capital T. If you just want a shortcut from here on out, right? So here's kind of our general form. Period is the time it takes total divided by the number of cycles or rotations. And super simplified, period is equal to 60 divided by our RPMs, rotations per minute. Right? This is not given on the formula sheet, but you'll end up using it a whole bunch, and you'll need to remember it for lots of different types of problems. So if you're ever given rotations per minute, right, you can right away throw it into this formula and solve for period, right? Or you can work through it logically, right? If we know that we have 3,600 rotations per minute, right, and we want to find how long it takes to do one rotation, we're going to divide, right, 60 seconds per minute by 3,600 rotations, and we'll get our seconds per rotation, which of course is our period. Okay, the question is not over. There's a little bit of sidetrack there, but the show must go on. We have our period of 1.667 times 10 to the negative 2 seconds. We're going to throw that into our general speed equation. where we're looking for radius. We're actually looking for diameter, but the equation is with radius. We'll have to get diameter later. So rearrange it to solve for radius, which is our speed times our period divided by 2 pi. Throw in everything we know. We've got 85 meters per second times 1.667 times 10 to the negative 2 seconds. So our seconds will cancel. We're left with meters on top divided by 2 pi. We get a radius that is equal to 0.2255 meters. And from here, we know diameter is twice our radius, which is twice of this 0.2255 meters, giving us 0.45 meters or 45 centimeters. That's the diameter of this centrifuge that is spinning our test tubes around. Okay, let's take a look at acceleration. So centripetal acceleration will always be written like this with a little subscript c. So keep your eyes open for that little c. That'll tell you we're working with a new type of acceleration, our centripetal acceleration, which isn't changing the magnitude of the speed or the velocity, but it's only changing the velocity's direction. So it's the rate of change of our velocity's direction. So how quickly, this is a nice comprehensive definition, how quickly the direction of our object's motion changes. Right, so even though we have constant velocity, or constant speed I should say, our direction is constantly changing, giving us this centripetal acceleration. And we get two new formulas given on our formula sheet for centripetal acceleration. We either have our speed squared divided by the radius, or we have this big long one derived from our circumference squared, right? So 4 pi squared r divided by period squared. So you're given these. I won't get into the derivation of them. If you break out the units for each of these, we would get meters squared per second squared divided by meters, which becomes meters per second squared. Perfect. Here we have 4 pi squared with no units. We have meters up top, and we have period, which is seconds per rotation, right, where the rotation kind of becomes irrelevant. So it's meters per second squared. Right, and yeah, here's just a breakdown of those three variables you'll see in our centripetal acceleration formulas. All right, direction. The centripetal acceleration is always directed towards the center, so it is center seeking. So it's always pointed towards the center. You can see here all three of those centripetal accelerations. Doesn't matter where our object undergoing uniform circular motion is in its path, the centripetal acceleration is always directed to the center, center seeking. So by definition, if that is pointed to the center, that means it's going to be perpendicular to our velocity, right? So you'll always have centripetal acceleration perpendicular to our object's velocity vector. Okay, our final question for the lesson 1. We have given centripetal acceleration. We know that the speed is tripled and the radius is doubled. So we're going to be working with this formula here. So we're basing this on centripetal acceleration, which is equal to speed squared over radius, because they're not telling us anything about period. So we can't use that definition or formula of centripetal acceleration. So from this formula, they are then telling us, or we can see that centripetal acceleration is proportional to the speed squared, or the velocity squared. So if our speed is tripled, that means our centripetal acceleration is actually times 9, or 3 squared. So tripling the speed will actually increase the centripetal acceleration 9-fold. And we're also adjusting the radius, which is inversely proportional. So if our radius is doubled, multiplied by 2, then our centripetal acceleration is multiplied by 1/2. So bringing this all together, so if we started with AC, we're then replacing our speed with 3 times. So that would be 3v squared divided by our radius, which is twice as much. We end up with 12, or sorry, we have 9 divided by 2, which is going to be multiplied by our starting acceleration. So we started with 12 meters per second squared. Is equal to 9/2 of our starting acceleration. Sorry. We're going to take our 12 meters per second squared. We're going to multiply it by 9 from our speed that's being increased by 3. And we're also going to multiply it by 1/2, which gives us 54 meters per second squared. So that's the new I'm using a new symbol. It's a prime. That means that it's the new or the changed one, right? Or you could call it AC, new, which is equal to our original times 9 from the speed times 1/2 from the radius. So again, just working with proportionalities, which can be a little tricky, right? My advice is just to either work through it step by step with each variable, or to replace our standard equation with how they're changing, right? So that would become 9/2, and you're going to multiply your original by 9/2. All right, let me know if you have any questions. I'll see you for our second lesson in U5.